So, dear students, till now, the topics that we have discussed concentrated on the experimental aspect of chemical kinetics. It may be determination of order of the reaction or rate constant of the reaction. So, in today's class, we will move to uh, studying and understanding the various theories that were proposed to explain the rate of a chemical reaction. Okay, so different theories were proposed to give an insight into how a reaction proceeds. The theories, certain theories were proposed based on the viewpoint of the macroscopic nature or the bulk nature of the system, whereas some theories were proposed keeping into account the microscopic nature or the molecular level nature of the system. What do you mean by that? In some theories, it was assumed that it is the overall behavior of the entire system, the bulk behavior, that is the behavior of a large number of molecules, that affects the rate of a chemical reaction. And in certain theories, it was believed that it is in fact the molecular level property that decides the rate of a chemical reaction. So it is the nature of the molecule and its structure and its energy that affects the rate of the chemical reaction. But the truth is, both the factors, both the macroscopic as well as the microscopic nature of the system influences the rate of the reaction. So one such theory that was proposed by Arrhenius is considered as a very important theory. Though this theory is very simple and it has its own limitation, it is not the complete theory, but it is a very good theory we can consider this as a starting point, okay, for the various theories of chemical kinetics. As I already told you, temperature is one of the important factor that affects the rate of the reaction. So many theories were proposed to explain the temperature effect on the reaction rate. So one such theory was given by Arrhenius. Though different theories were proposed by different people, the picture or the interpretation that was given by Arrhenius is still now considered as the most proper or appropriate interpretation. That is why we consider Arrhenius theory as a very important starting point. Okay, so before going to Arrhenius theory or any other theory related to Arrhenius theory, first let us try to understand how the energies between a large number of molecules are distributed in a system. So for example, if I have a system, okay, a closed system having total energy E at a temperature T, and it contains total number of molecules equal to N. So the average energy of the system is nothing but total energy divided by total number of molecules. So our discussion on statistical thermodynamics in previous semester, okay, we have already realized that though all the molecules in the system are identical, they will not have same energy. E bar is equal to E by N. So all the molecules will not have the same energy equal to the average energy. Certain molecules will have energy less than average energy, and certain molecules will have energy much greater than average energy, and most of the molecules will have energy in and around very much close to the average energy. And as the temperature increases, the energy, total energy of the system increases, and therefore the average energy also increases. Now at a particular temperature T, okay, where T is above 0 Kelvin, absolute 0 Kelvin, the molecules are in continuous motion, and when the molecules are moving randomly, they always collide with each other, and when they collide with each other, there is exchange of energy between the molecules. So a molecule initially having higher energy, on collision it may lose some of its energy, so it will immediately jump from higher energy side to lower energy side. Similarly, a molecule which is having very less energy than the average energy, it may gain some energy on collision, and it may move from lower energy side to higher energy side. So in any system, due to the collision, there is continuous exchange of energy between the molecules. So there is some sort of equilibrium associated with higher energy molecules and the lower energy molecule. A lower energy molecule at any instant of time may become higher energetic molecule, or an higher energy molecule may become lower energetic, okay, due to collision. So if I plot, okay, if there are different ways in expressing the relation. You have Maxwell Boltzmann distribution, we have Fermi Dirac, we have Bose-Einstein distribution. So let us consider the simplest one among them, that is the Maxwell's Boltzmann distribution. So if I plot a graph of the number of molecules having a particular energy versus the energy, okay, so I am plotting a graph of the number of molecules having a particular energy in the system versus the energy. Then the nature of the graph will be something like this, so this energy which corresponds to this peak is nothing but the average energy of the system. So you can see that there are maximum number of molecules that are having energy equal to average energy, or you have large number of molecules which are having energy very much closer to the average energy, and you have few molecules which are having energy very much lesser than average energy. There are only lesser number of molecules. Similarly, there are a few lesser number of molecules having energy much greater than the average energy. So this is the Maxwell's Boltzmann distribution plot, okay. This is called as a bell shaped curve, and this is at the temperature, say for example T1. So the average energy, I will take it as E1, and N1 responds to the total number of molecules that has energy equal to the average energy, okay, and that is the maximum number of molecules corresponding to this particular energy. Now if I increase the temperature of the system from T1 to T2, what happens to the total energy? The total energy increases, and therefore average energy also increases. Why? Because E increases. N is a constant, but E increases, so average energy also increases. So if I plot, okay, now the diagram would be like this. Okay, so this diagram, the second diagram I have drawn, it corresponds to temperature T2. So we can observe certain important differences between the two curves at temperature T1 and T2. The first is this curve, the peak of this curve has shifted to right hand side. Why? Because the average energy of the system has increased as we increase the temperature from T1 to T2. So here E1 bar is less than E2 bar. The average energy at temperature T2 is greater than E1 bar, okay. And also what we observe is this curve is above this curve. This is corresponding to T2, this corresponds to T1. So at higher energy spectrum, okay, you can see that the curve corresponding to T2 is much greater than the curve corresponding to T1. So what does it indicate is at higher temperature there will be more number of molecules having greater energy than average energy. I repeat, as you increase the temperature, okay, the average the average energy of the system increases, and at the same time the number of molecules having much higher energy than the average energy also increases, okay. So if I take, I will take some energy, okay, some energy, random value E star, I will call it as E star, some energy E star, okay. Now if I ask what is the fraction of the total number of molecules that has energy greater than E star? What is the fraction of the number of molecules that has the energy greater than this energy E star? That is given by, I will write here, so the fraction of the number of molecules having energy greater than some energy. Okay, E star is e to the power minus E star divided by k into T, where k is the Boltzmann constant, T is the temperature, and E star corresponds to this energy, some energy E star. So this is the fraction of the number of molecules. So what is the total molecules? Total molecules. The total number of molecules will be n into e to the power minus E star divided by k into T. So this number represents the total number of molecules having energy greater than some energy E star. Okay, all these expressions are obtained from the Maxwell Boltzmann distribution. So the fraction of the total number of molecules having energy greater than some energy E star is given by e to the power minus E star divided by kt, and if this fraction is multiplied by the total number of molecules present in the system, that would give the total number of molecules having energy greater than energy E star. And if I shade this area, okay, if I call this as A, okay, I will take this some point here, B, okay, I will call this as C, D, E, F, okay, I will shade this area. So I have two area, one is area A, B, C, D, a smaller area A, B, C, D corresponding to temperature T2, and another you have a larger area A, E, B, F, which corresponds to temperature, oh sorry, I made a mistake here, sorry. You have two areas, one is A, E, F, B, A, E, F, B corresponding to T2, that is the area under the curve corresponding to T2. Another area is C, E, F, B, which is the area below the curve at temperature T1. And you can clearly see that the area AEFB corresponding to temperature T2, this temperature, this area is much greater than the area corresponding to curve corresponding to temperature T1. So AEFB area AEFB is greater than the area CEFB. What does it mean? It means that the number of molecules having an energy greater than some energy E star will be more, okay, as the temperature is increased. So greater the temperature, greater would be the number of molecules having energy greater than E star. Okay, so these are some of the background knowledge that we would require when we try to interpret Arrhenius theory. So from Maxwell Boltzmann distribution, it is now very clear that the energy is not equally distributed among the molecules. Some molecules are having very lesser energy, some molecules are having very higher energy, and most of the molecules will have energy closer to the average energy. So as you increase the temperature, the overall energy of the system increases, that is the average energy increases, okay, and that there are more number of molecules having higher energy, that is explained in this area. Okay, so this is a very important point that we have to remember. And please remember this equation: the fraction of the number of molecules having energy than some energy E star, okay, is e to the power minus E star divided by k into T. Or you can calculate the number of molecules, it is n into e to the power minus E star by kt. So this is the number of molecules having energy greater than E star. Now let us go back to Arrhenius theory. So Arrhenius was not the first person, okay, who explained the effect of temperature on the rate of the reaction. So the exact effect of temperature on the rate was studied by several scientists, several people. I will highlight the work of only few. Okay, in 1862, okay, in 1862, one of the significant work, okay, that was carried was by a scientist named uh, Berthelot. Okay, Berthelot. Okay, he established and proposed an equation for rate constant of a reaction as K is equal to some constant A into e to the power d into t. So he proposed an empirical relation between rate constant K and temperature T, as K is equal to A into e to the power d t, where A and D are constants. Okay, A and D are constants. But the equation that he proposed was not consistent with the experimental results. So in some experiment for some chemical reaction, okay, this equation gave a consistent explanation, but for most of the chemical reaction this equation did not give a consistent explanation. So there was no consistency between the theoretical and the experimental results. So this equation was further modified later by Van't-Hoff. Okay, so this is a very important contribution, because Van't-Hoff, even though the final version that we use is not the one given by Van't-Hoff, but still this is very important, because it was the Van't-Hoff equation that was borrowed by Arrhenius for explaining his theory. So what did Van't-Hoff actually propose? The equation by Van't-Hoff is very simple. So let us consider a reversible reaction. Okay, so let us consider a reversible reaction such as A plus B giving C plus D, where K1 is the rate constant of the forward reaction, K minus 1 is the rate constant of the backward reactions, and these reactions are very simple. Van't-Hoff, okay, he thermodynamically proved that the equilibrium constant of the reversible reaction varies with the temperature according to the equation d ln K divided by dt at constant pressure is equal to delta U naught divided by RT square. So this is nothing but the well-known equation you have studied in thermodynamics, Van't-Hoff equation. Okay, so there you might have used delta H naught, which is the standard enthalpy of the reaction. Okay, so here we have written standard internal energy of the reaction. So this is a well-known equation derived by Van't-Hoff in thermodynamics called as Van't-Hoff equation. This equation gives the relation between the equilibrium constant and the temperature. So how the equilibrium constant of the reaction varies with temperature. So delta U naught is the change in the energy of the reaction. Okay, now the rate of the forward reaction is, okay, I will rub this off now. Please remember this. The rate of the forward reaction, is, okay, RF is rate constant K1 into concentration of A into concentration of B. Similarly, the rate of the backward reaction, okay, RB is the rate constant K minus 1 into concentration C into D. And any reversible reaction finally reaches the state of equilibrium. And at equilibrium, the rate of forward reaction will be equal to rate of backward reaction, that is K1 into A into B is equal to K minus 1 into C into D, which on rearrangement we get therefore concentration of C into concentration of D divided by concentration of A into concentration of B, okay, is equal to K1 divided by K minus 1, that is rate constant of forward divided by rate constant of backward. Since these concentrations of reactants and products corresponding to equilibrium, I will write a subscript EQ, because these concentrations are at the equilibrium. So this ratio is nothing but the equilibrium constant K. This is the equilibrium constant K. So how do you define the equilibrium constant? It is the ratio of the rate constant of forward reaction divided to the rate constant of the backward reaction. So what now we'll do is we will substitute equation 2 in equation 1. In equation 1 I have equilibrium constant K, and now we know that equilibrium constant K is K1 divided by K minus 1. So substituting equation 2 in equation 1, we get d ln K divided by K minus 1 divided by dt at constant pressure is equal to delta U naught divided by RT square. Okay, or if I use the rule of logarithm and differentiation, and for the sake of simplicity I will not write this condition. I will simply write it as d ln K divided by dt minus d ln K minus 1 divided by dt is equal to delta U naught divided by RT square. Okay, delta U naught divided by RT square. Now what it want of argue is, since the equilibrium constant is influenced by certain energy, okay, delta U naught, the equilibrium constant is influenced by some type of energy, that is delta U naught. Therefore he argued that these rate constants should also be affected or influenced by some types of energy. So the rate constant of the forward reaction should be influenced by some energy E1. Similarly, the rate constant of the backward reaction should also be influenced by some type of energy E minus 1. So the argument is very simple. ಯಾಕಂದ್ರೆ ಈಕ್ವಿಲಿಬ್ರಿಯಂ ಕಾನ್ಸ್ಟೆಂಟ್ ಈ ಡೆಲ್ಟಾ ಯು ಎನರ್ಜಿ ಮೇಲೆ ಡಿಪೆಂಡ್ ಆದ ತರನೇ ರೇಟ್ ಕಾನ್ಸ್ಟೆಂಟ್ಸ್ ಕೂಡ ಯಾವುದೋ ಒಂದು ಎನರ್ಜಿ E1 ಮತ್ತು E-1 ಮೇಲೆ ಡಿಪೆಂಡ್ ಆಗಿರಬೇಕು. ಸೊ ಬೇಸ್ಡ್ ಆನ್ ದಿಸ್ ಆರ್ಗ್ಯುಮೆಂಟ್, ಓಕೆ, he split this equation, he split the LHS of this equation as, therefore d ln K divided by dt is equal to E1 divided by RT square. So the first term of this equation can be written as d ln K divided by dt is equal to E1 by RT square. See, this expression is similar to this delta U naught by RT square. This is based on a argument. So equilibrium constant ಯಾವ ತರ ಎನರ್ಜಿ ಮತ್ತೆ ಟೆಂಪರೇಚರ್ ಮೇಲೆ ಡಿಪೆಂಡ್ ಆಗಿರ್ತದೆ, ಅದೇ ರೀತಿ ರೇಟ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಕೂಡ ಯಾವುದೋ ಒಂದು ಎನರ್ಜಿ ಮತ್ತೆ ಟೆಂಪರೇಚರ್ ಮೇಲೆ ಡಿಪೆಂಡ್ ಆಗಿರಬೇಕು. ವಾಟ್ ಈಸ್ ದಿಸ್ E1? I don't know. So some energy E1. So similarly for the reverse reaction, that is the backward reaction, you can write the second term d ln K minus 1 divided by dt is equal to E minus 1 divided by RT square. So these two equations, okay, combined, I will call it as equation 4. Now you can clearly see that if I substitute this equation here, you can see that therefore E1 minus E minus 1 is related to delta U, that is the change in internal energy of the reaction. Okay, change in internal energy of the reaction. Now what did want of propose is that this delta U naught, the change in the energy, is independent of temperature. Okay, in most of the cases delta U naught should be independent of temperature. Okay, sorry, dependent on temperature. So similarly, therefore E1 and E minus 1 should also be dependent on temperature. I repeat, according to want of, the delta U naught for a chemical reaction should depend on temperature. So ಅದೇ ರೀತಿ energy E1, that is related to the forward reaction, and energy E minus 1, that is some type of energy related to the backward reaction, they should also be dependent on temperature. In an event, suppose if E1 and E minus 1 were temperature independent, okay, what is the general assumption? That E1 and E minus 1 depends on temperature. Suppose they are not dependent on temperature, then what happens? In such case, suppose the energy factor E1 and E minus 1, the energy factors related to the forward and the backward reactions are temperature independent. Okay, so suppose they are temperature independent, what we can do is we can simplify equation 4. Okay, equation 4, we can integrate equation 4 with respect to temperature keeping E1 as a constant. Okay, similarly we can integrate this equation 4 with respect to temperature keeping E minus 1 as a constant. ಯಾಕೆ E1 ಮತ್ತು E minus 1 constant ಅಂತ ತಗೊಂಡಿದ್ದೇವೆ? Because we are assuming that they are not dependent on temperature. So if I integrate equation 4 for forward as well as the backward reaction, we get K1, that is the rate constant of the forward reaction, as some constant A1 into e to the power minus E1 by RT. Similarly, for the backward reaction, K minus 1 is equal to A minus 1 into e to the power minus E minus 1 divided by RT. So in general, for any reaction, the rate constant can be written as K is equal to A into e to the power minus E divided by RT. Okay, so this was the equation that was given by 1/2, which gives a relation between rate constant and the temperature of the reaction. So the rate constant of a reaction according to 1/2 depends on some constant factor A, which is unknown. Okay, and it depends on the temperature, and it depends on some type of energy that is related or associated with the chemical reaction. So this equation, now you know it in a well known form, which is called as Arrhenius equation. But remember, the original equation was not given by Arrhenius, it was derived by 1/2. So this equation was given by 1/2 based on thermodynamics. So using different thermodynamic consideration that we discussed now, so he obtained this equation. But the problem that he faced was, even though he derived and obtained an equation for the relation between rate constant and temperature using thermodynamics, he was not able to justify the physical meaning of this equation. So he was not able to explain what is this energy E that is associated with the reaction. So mathematically this equation is true, this is correct, but he was unable to give a physical picture for a chemical reaction. So how the chemical reaction is actually proceeding. Okay, what is this energy E? Why this you are getting an exponential negative form of energy? So what is the exact meaning of this equation? He was unable to explain. Okay, so the explanation for this equation was given by Arrhenius. So Arrhenius used the Maxwell Boltzmann distribution that I explained earlier, and using that explanation and also using the 1/2 equation, he gave a physical interpretation of exactly how temperature affects the rate of the reaction. So though this equation was given by 1/2, this is now called as Arrhenius equation because the physical interpretation was given by Arrhenius, which is now accepted. So let us now try to understand what Arrhenius or how Arrhenius justify this equation. So Arrhenius gave a physical interpretation for the energy E. So this energy E term that appears in the equation, 1/2 was unable to explain what is that energy. Arrhenius was able to give a justification to this energy E. So what he called this energy E is as energy of activation or activation energy of the reaction. So according to Arrhenius, this E is nothing but the activation energy of the reaction or the energy of activation. So he rewrote equation 5 as so what he did is he rewrote the equation as, so according to Arrhenius, K is equal to A into e to the power minus EA divided by RT. Okay, so the only change he made here is instead of E, he wrote it as EA, where EA is nothing but the activation energy, and the constant A is now called as Arrhenius factor, okay, or collision factor. Now, and also it is sometimes called as pre-exponential factor. Okay, this A is also called as pre-exponential factor because this term A appears before the exponential term, that is why it is called as pre-exponential factor. And according to Arrhenius, both A and EA are independent of temperature. So let us try to understand what is the physical justification that was given by Arrhenius. So according to Arrhenius, only those molecules participate in the chemical reaction that are suitably activated. I repeat the sentence. According to Arrhenius, only those molecules participate in the chemical reaction that are suitably activated. The molecules can become activated by acquiring energy through collision. This I already told you when I explained about Maxwell Boltzmann distribution. How do molecules get energy or lose energy? The molecules either gain or lose energy during collision. So in this case, a molecule with less energy can become activated by acquiring energy through collision. So you have two type of molecules in a system or in a reaction mixture. One is a passive molecule and another is a active molecule. So for every chemical reaction there is a minimum energy called as threshold energy. So for every molecule there is a minimum energy called threshold energy that is represented as E star. So those molecules having energy lesser than the threshold energy are called as passive molecules, and the molecules that are having energy greater than the threshold energy E star are called as active molecules. And there is a equilibrium, and there is an equilibrium between the molecules, the passive molecules and the active molecules, where M represents the number of molecules. So there is a uh, uh, M represent a molecule. So there is an equilibrium existing between passive and active molecule. What does it mean? What does this equilibrium mean? A passive molecule may become activated at any instant of time, okay, by acquiring energy through collision, or a active molecule may become passive by losing energy during collision. So there is a equilibrium between the passive molecule and active molecule, and the temperature, okay, and the temperature has an effect on this equilibrium. If I increase the temperature, if you remember the bell diagram that I have drawn here, where I explained that as the temperature increases, the number of molecules having higher energy also increases. So as we increase the temperature, what happens to this equilibrium? The equilibrium shifts towards right, that is more and more passive molecules will become active molecules. On the other hand, if I decrease the temperature, the equilibrium will shift towards left, that is the active molecules will become passive. So the temperature affects the equilibrium constant of this reaction. And how does it affect the equilibrium constant? It affects the equilibrium constant of the reaction as given by the want of equation, the equation number 1 that I explained in the previous slide. So the temperature affects this equilibrium according to want of equation, which is d ln k divided by dt is equal to delta u naught divided by RT square. So increasing the temperature shifts the number of molecules towards activated side. So the rate of the reaction should be proportional to the number of active molecules. Greater the number of active molecules, so greater would be the rate of the reaction. And how to get more number of active molecules? That is by increasing the temperature. So as I increase the temperature, the number of active molecules also increases, therefore the rate of the reaction also increases. So the interpretation given by Arrhenius is very simple. So for every reaction, for every chemical reaction, okay, there is a minimum threshold energy. There is a minimum threshold energy. I will call it as E star. Okay, that's a minimum threshold energy called as E star. If the molecule has energy E greater than E star, that is active molecules, okay, then such molecules can undergo chemical reaction. So if the molecule is having an energy greater than its minimum energy called as threshold energy, then such molecules are called as active molecules, and such molecules can participate in the chemical reaction. If the molecule has energy E less than the threshold energy, that is called as passive molecule, then they do not participate in the reaction. So they are not having sufficient energy to undergo the chemical reaction. So if the molecules are properly activated and they are having an energy greater than some threshold energy E star, okay, the value of E star depends on the chemical reaction. So if the molecule is properly activated and has energy greater than E star, then it can undergo a chemical reaction, and if the molecule has energy lesser than E star, it cannot participate in the chemical reaction. Okay, and you can at any instant of time increase the number of activated molecules by increasing the temperature. As I already told you, as I increase the temperature, this equilibrium gets disturbed towards the right, it shifts towards the right. As you increase the temperature, there will be more number of activated molecules. So increasing the temperature increases the number of molecules having energy greater than the threshold energy E star. And in from Maxwell Boltzmann distribution, I already gave that expression that the number of molecules having energy greater than a certain energy E star is given by n into e to the power minus epsilon star divided by kt. Okay, not E star, epsilon star. There I used epsilon star. So remember the Maxwell Boltzmann distribution that I explained earlier. ಅಲ್ಲಿ ನಾನು ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಿದ್ದೇನೆ, ದಿ ನಂಬರ್ ಆಫ್ ಮಾಲಿಕ್ಯೂಲ್ಸ್ ಹ್ಯಾವಿಂಗ್ ಎನರ್ಜಿ greater than some energy epsilon star is given by n into e to the power minus epsilon star divided by kt. And you see that this equation is somewhat similar to the term e to the power minus ea by rt. So the only difference is here E star has now become ea, and activation energy denominator is one and the same. The only difference is here you have Boltzmann constant, here you have gas constants. They are related to each other through Avogadro number. So you are getting a similar expression in both the cases. So this validates the Arrhenius explanation. So Arrhenius explanation is very simple. For a molecule to undergo chemical reaction, it should first acquire a minimum energy called as threshold energy. If the molecule acquires that minimum energy called threshold energy E star, then that molecule is said to be activated and it can undergo a chemical reaction. If the molecule is sufficiently not activated, that is if its energy is less than the threshold energy, then it cannot undergo the chemical reaction. And how can you make more number of molecules undergo the chemical reaction? You can make that by increasing the more number of activated molecules. And how do you increase the number of activated molecules? That is by increasing the temperature and shifting this equilibrium to the right. So Arrhenius gave a very simple equation interpretation to Arrhenius to this equation. So let me draw a diagram which is called as potential energy curve or energy curve. Okay, I will not say potential energy, it is an energy curve. Okay, that was given by Arrhenius. So according to Arrhenius, so if I plot a graph of energy versus reaction coordinate. Energy versus reaction coordinate. What is reaction coordinate? We will explain later when we study transition state theory. So we are plotting a graph of energy versus reaction coordinate. So this point represents the energy of the reaction, and this point somewhere here represents the energy of the product. Okay, you can plot it other way down. Okay, you can write energy of the reactant as lesser than energy of product. Anyway, both are one and the same. So according to Arrhenius, there is some barrier. Okay, there is some barrier, a imaginary barrier between the reactant and the product. So only those molecules which can cross that barrier, which can cross that hill, only those molecules can pass on to form products. So it is simply like crossing a hill. If you are on one side of the hill and if you want to go to the other end, then you have only one option, that is you have to climb the hill. That is you have to acquire energy, climb the hill and pass on to the other side. So here also he assumed that there is some type of barrier between the reactant and the product, and only those reactant molecules which acquire sufficient energy to cross that barrier will undergo chemical reaction. If the molecule do not have sufficient energy, they do not undergo chemical reaction. Okay, and that minimum energy the molecules should acquire to go undergo a chemical reaction is called as threshold energy. Okay, this is called as threshold energy. So there is a barrier between the reactant and the product. So this energy is nothing but the threshold energy. Now the difference, this difference is the very important parameter. This is the energy of the reactant molecule. This is the minimum energy the molecule should have. So already this is zero of energy. So already the reactant molecule is having some energy ER. Now it has to acquire some extra energy other than ER to reach this threshold energy. That additional energy is nothing but called as activation energy or energy of activation. So the threshold energy and energy of activation are not same, they are different. Threshold energy is the total energy the molecule should have to undergo a chemical reaction. What is activation energy? Activation energy is the excess energy the molecule should have to reach threshold energy. Already the molecule is having some energy ER, it should gain some extra energy due to collision to reach this threshold energy, to reach this height or barrier, and that extra energy, minimum extra energy, is called as activation energy. So this is the activation energy for the forward reaction. This would be the activation energy, write it as E minus A for the backward reaction. So the molecules, if it wants to cross this barrier, it has to acquire an additional energy called as activation energy, and greater the activation energy, okay, lesser will be the rate constant. So greater the height of this barrier, it means the molecule has to struggle to gain that activation energy. It has to undergo a lot of collision before it gains that activation energy. So such reactions will be very slow because it will take a lot of time, okay, for the molecule to acquire this energy. So if the activation barrier is very high, so if the activation energy of a reaction is very high, rate constant will be very slow, or the rate will be very slow. On the other hand, if the activation energy is very less, that is the height of this barrier is very less, then any molecule can easily pass through the barrier, okay, by acquiring that minimum energy. In such case, the rate of the reaction will be very large. So Arrhenius gave a very beautiful meaning or interpretation to this equation that was given by Want of. Though Want of derived this equation, the credit is given to Arrhenius because he was the one who actually explained how a chemical reaction would proceed, okay, when you change the temperature, okay. But this, though this is a very simple picture and it explains the effect of temperature, there are many limitations for Arrhenius theory. In fact, the list of limitation is very much greater than the list of success of this theory. But still this is an important theory because it acts as a starting point for other theories. So what are the limitations of this theory? There are three important limitations. The three important limitations are the three important limitations are the first is the first limitation is, now what is this activation energy? Because a molecule can have different type of energy. A molecule can have kinetic energy, a molecule can have potential energy. If the molecule is much complicated, it will be rotating, it means it has rotational energy. It may be vibrating, it means it has vibrational energy. The electrons are revolving around the nucleus, and a molecule has an electronic energy. So this, when I say a molecule is activated, which energy component is actually getting changed, whether it is the kinetic energy, whether it is the potential energy, whether it is the rotational energy, or whether it is the vibration energy. So there is no information about the characteristic of activation energy. So the activation energy means which type of energy. Okay, that justification is not given by Arrhenius theory. So the energy of activation is not properly justified by Arrhenius. Okay, that is, this energy, okay, is related to which component of the molecular energy. This energy is related to which component of the molecular energy is not answered. So when I say the molecule is activated, it means it is having some extra energy. ಆ extra energy ಅಂತ ಏನಿದೆ ಅದನ್ನು ಯಾವುದರ ಜೊತೆಗೆ ಲಿಂಕ್ ಮಾಡಬೇಕು, whether it is related to the vibrational motion of the molecule, whether it is related to rotational energy of the molecule, whether it is related to kinetic energy or potential energy. Molecule is activated, how it is activated, whether it is rotationally activated, vibrationally activated, translationally activated, there is no explanation given by this theory. The another is, it says that the molecule has to pass through a barrier called as energy barrier. Okay, this molecule, this state is nothing but called as activated. Okay, this position represents an active molecule, this represents passive molecule. So there is an equilibrium between active molecules and the passive molecules. So these are all passive molecules because they do not have sufficient energy, and there is an equilibrium between passive and active molecule. So a passive molecule can become active, or an active molecule can become passive. But what is the structure of this active molecule? Okay, how this active molecule is structure wise different or similar to the passive molecule. So there is no explanation or details about the structure of the active molecule. So what type of species exactly exist at this peak, there is no information about the structure of the active molecule. So there is no details about the structure of active molecule. Okay, and later when we study another theory called as transition state theory or activated complex theory, we see that the structure of that active molecule is very important in understanding the overall rate of the chemical reaction. The third important limitation of this theory is the rate constant predicted by this theory is much greater than the experimental value. So the value of the rate constant that is calculated by using this equation theoretically is much greater than the experimental value. So no way we can reduce the value of rate constant by making any modification to this equation. So that is an important limitation of Arrhenius theory. Okay, so though this theory has several limitations, it has certain advantages. Okay, the advantages is, even in spite of having so many limitations, it is possible to determine experimentally what is the activation energy of the reaction. So in the next video we will discuss about the two methods through which it is possible to experimentally determine the activation energy of a chemical reaction.